Welcome to another class of Survey of Physical Sciences. And in this chapter, the chapter 19, we're gonna keep building the Earth's surface. We're gonna keep understanding how, these features that we observe on the crust are formed and what are the geological events behind them. So the idea, is just keep talking about how this crust that covers the Earth is in constant change, okay? Helping to build up this surface that we are stepping on. Before we move on into some of the deep concepts, I wanted to bring this idea of principle of uniformity that tells us that, the Earth's history could be understood, could be interpreted by tracing backwards. So you look at the present to understand what happened in the past. So this principle of uniformity tells us that the same geological or geologic processes that are occurring to the rocks today, they were also present or they also occurred in a distant past. Okay, so that is to say that the rocks that we have today, they are changed by the same processes that changed them in the past. Okay, of course, those processes, they probably didn't happen at the same rate. So maybe they occurred faster or slower, or maybe there were some other catastrophic events that contributed to this to shaping those rocks, okay? But, excluding the fact that catastrophic events can occur, we can understand we can understand that the history, right, of Earth's surface by looking to what happens to the rocks of today, because that tells us what happened in the past. I said that, we can exclude these catastrophic events, but, the principle of uniformity doesn't actually need to exclude these catastrophic events because they are part of what happens to the surface. Maybe we don't suffer the same catastrophic events that Earth suffered in the past, okay? But we can still look at that rock and understand how that Earth was in the past. Okay, so the process of changing the Earth's crust is called diatrophism. Okay, so that is the process that, generally it's like a big umbrella that we're gonna study concepts that can be fit under this umbrella. Would is defined as those processes that deform the Earth surface. Okay, these processes, they can produce structures such as plateaus, mountains. We're going to take a look at mountains in this class. Folds as well. We're also going to take a look at these folding structures that help making the mountains. These changes are also related to volcanic activity, right, which is the movement of magma, and even earthquakes. All right, not earthquakes like I said before in the other class. But here, the idea that that the Earth is constantly changing, it's because these plates, they exist and they are being pushed against each other. Okay. There are two main concepts that we also need to understand, and they are stress and strain. So stress is the force tending to compress, pull apart, or even the form a rock. Okay, there are three main types of stress forces. There are compressive stresses, which is when the plates are moving together or the rocks are moving together. We have the tensional stresses. The tensional stress is the opposite of compressive stress because in the tensional, the plates are moving apart. Okay, and the other type of stress is the shear stress, when the plates are sliding past each other, which we call, the transformative boundaries in our last last chapter. Okay. However, even if the rock is submitted to those stresses, either compressive, shear, or tensional, the rock can either not change, so the rock can withstand that stress and doesn't change at all. The rock can either, suffer or show a elastic change, can either show a plastic change when there is no recovery of that rock to its original shape, or can break completely because of the high pressure submitted to that rock. This adjustment of the rock and of the plates to the stress is called strain. So, like I said, there are a few main types of these strains. So there is the elastic strain, which is when the rock or plate will return to its original shape. We have after the stress is released. We have the plastic strain, which is when there is no recovery of that rock or that plate after the stress is released. So, the final result is a molded or bent surface. And there is a fracture strain when there's finally a crack in those rocks, and those rocks will eventually break. You can think of that as a can of soda, right, which is made of aluminum. So, sometimes you can, if you are very gentle to that soda can, you can press it and the soda can will return to its original position, right? So you pressing that can is what we call a stress. It would be a compressive stress, okay? The fact that the can goes back to its normal position, then it's a elastic strain. However, if you compress too much that can to a point where that can now is bent and doesn't go back, then we call that plastic restraint. If you, depending on how strong you are and keep adding stress to that can eventually will rupture, will break, okay? All right, so moving on, we're gonna talk about some of these forces kind of molding the surface of Earth, okay? The first event I want to talk to you is the feature called folding. Folding happens when, for instance, we studied the sedimentary rocks when we talked about rocks, and I just assumed that those sediments are usually positioned in flat layers, right, which are usually horizontally placed one on top of each other, okay? However, because of these, stresses, especially the compressive stress that the rocks are submitted, that those layers can be bent, okay? So when the layer bends, we call that bend of fold, okay? So folds are the bends that happen to the layered bedrock. You can think of that as the rug in your living room, for instance. Okay, so the rug is usually laid flat by your parents or whoever maintains your house, or even by yourself. But then, if you, depending on how you step on that rug, you will create some folds, right? So if you apply some compressive stress to that rug, you're going to fold that rug into other positions. And that can happen to some of the sedimentary rocks as well. So those sedimentary rocks, they can fold, okay? And they can produce domes or basins. Domes is when the bulging of that fold is located or is oriented upwards. And basins is when the bulging fold is located downwardly. Okay, so if you think of these two examples, this is what I mean, right? So when you have this arc-shaped structure, this is also called anticline, all right? But this is a type of dome, and when you have this through-shaped structure, then this is a basins, or also called syncline, all right? So, this folding can change the way those mountains and those rocks they look like. So it's a way that Earth, a way by which the Earth can change its crust. All right. Some examples here, just so you guys know what I'm talking about. I don't think I'm going crazy yet. Is the Appalachian Mountains are kind of like this structure. Okay, so the Appalachian Mountains are this arch-shaped structure that we call anticline. So mainly what happened there with the Appalachian Mountains is that the sediments were, deposited on that floor, and then as the tectonic plates were moving, that folding occurred and moved all those sediments upwardly. Okay, so moved the Earth's crust towards the top. Mainly of the Appalachian Mountains, they are formed by sedimentary rocks, but some portions of the Appalachian Mountains are also you can find some metamorphic and igneous rocks as well. But most of it is essentially sedimentary rocks. I think you can find metamorphic and igneous rocks around, actually around our area. So around the Blue Ridge and the Piedmont regions is where you can probably find some metamorphic and igneous rocks in the Appalachian Mountains. Okay, here one example of this other structure is the I think it's in California, the San Joaquin Valley. So the San Joaquin Valley is a type of folding as well that happened downwardly. Okay, as you can see, the layers here, they are different in ages. The bottommost layer is usually older and the topmost layer is usually the youngest. Okay, even though we have this folding process generating these mountains or valleys, we can never exclude that erosion can happen, weathering can happen, and some other activities can happen. So I like to think that all the mountains that we are looking today, they are never in their final stage. So they are never completely mature because there's always change to those mountains. Another example of folding that we have here is, or a better example of this folding that you can observe is happening to this. Okay, so the Grand Canyon, for instance, is not a type of folding, but just an example of how the sediments are usually deposited in flat layers, okay, in horizontal layers, like we said. And but sometimes what can happen is this folding of those layers causing a structure like this. You can clearly see the difference between these layers, how they are deposited kind of horizontally to each other, one on top of each other, and how these were once like that. However, they suffered through, they went through this process of folding. Okay. The main rocks that you can find here in the Grand Canyon should be sedimentary rocks, mainly sandstone, I believe, and also shale and limestone are the main types of sedimentary rocks. But if I'm not mistaken, the bottommost, the deepest part of the Grand Canyon also has some metamorphic rocks, such as the gneiss. Okay, double check that information, but I'm also I am like 95% sure that the bottommost, the deepest portions of the canyon has gneiss, which is one type of metamorphic rocks as well. Okay, but again, mountains or valleys, they are never fully formed as long as there is water running through or erosion happening in that region. So folding is one process that can change the shape of these rocks and these mountains. But another process that can happen is a fault. A fault is produced by the movement of one block of rock against the other block of rock, against the rock that's in its opposite side. Okay, so here we have this representation, sorry, at the bottom figure where you have two blocks of rocks, and in the middle you have this fault, which is a crack in between that rock. Okay, and that can be produced by, for instance, an earthquake. All right, we're going to see in our next slide how that can happen. So the two masses of rock, they receive a name. So let's think that inside of this this mountain here, or these two rocks here, that there is the fault. I have someone inside of the fault plane, which is exactly the surface between those two big mountains. And let's imagine that I have someone right in between. When a person looks up above, when a person looks up facing the fault line, what the person will see is the hanging wall block. It's just like a nomenclature thing. And if the person looks towards its feet, so looking down, the person will see the foot wall block. Okay, it's just like a category for those two blocks that suffered this fault. Okay, so generally you can fold the mountain, or a fault can happen with those rocks. All right, a folding will create layers, and a fault is caused by this movement of the opposite sides of that crack. So this movement can be up or down, and we're gonna call that dip. This movement can also be horizontally, and that's a strike, or the movement can be oblique, which is the case here that we can see in these pictures when it happens in a sort of a diagonal plane. Okay, so usually earthquakes are related to causing these faults, right? Or earthquakes will cause this movement of one block of rock against the other, essentially. So the general meaning of an earthquake is the quaking, the shaking or vibration of the ground. That's the general meaning of an earthquake, which can be resulted from a sudden release of the energy from the stress on the rock. So let's imagine this three examples here. So here you have a big block of rock, okay? And then you have one stress coming from the left and one stress coming from the right. So you have stress being applied onto that rock, probably a type of compressive stress, okay? What happens is that, this stress causes some strain, right? Some adaptation of that rock to that stress. In this case here, let's assume that this rock doesn't actually go back to its original position, so we're going to call this a plastic strain. So if you keep, building up this stress, what happens is that the rock can break and causing a fault, and then in this process of breaking, the rock releases energy in the form of waves, energy in the form of vibration. Okay, so the vibrations are the seismic waves, and they will occur when the rock taking that stress fractures. All right, and then that causes this sudden movement of those blocks of rocks that are side to side of each other. These earthquakes, like I said, will generally occur along fault planes, but they can also cause fault planes, okay? Meaning that they can also cause other faults. Probably a very famous fault that you know is the San Andreas Fault that exists across the state of California, right? So this fault is located between the boundaries between the North American plate, which is on this side, and the Pacific plate, which is on this side. Okay, so there, you have two plates that are tightly together, and what's generally happening is that those two plates are causing some friction onto each other, and that friction usually prevents the motion of these plates. However, if the stress builds up, that can win over the friction force or even over the rock rupture strength. And then when that stress builds up and is stronger than this friction or this rupture strength, what happens is that the rocks, they snap suddenly into a new position, causing a movement. So it's as if they were settle into a new position. So these stressed rocks, they snap, causing these sudden movements, and the sudden movements cause vibrations, and those vibrations are felt as earthquakes. Okay, just putting everything together. This movement of snapping suddenly and then setting into a new position is called the elastic rebound. It's there is catastrophe, and then those rocks settle back again. So that's why it's called elastic rebounds. So earthquakes can be located and measured, right? So there are two features of these earthquakes. One is the focus. The focus is actually where that earthquake originates. So it's the actual origin of these seismic waves. So it's the center, okay, of that earthquake. And you have the epicenter. Epi means above the center. So it's the location on the surface's crust, which is directly located above the focus of the earthquake. Again, earthquake usually happens between the plate boundaries. All right, we can measure the strength, and we're gonna call that the magnitude of the earthquakes by using a seismograph or a seismometer. I think that's also the name of that instrument. So it's an instrument that is used to detect and measure the earthquakes. These instruments, they are responsible for, or they can detect, three types of waves. I think I mentioned these waves before in our previous classes, I believe. So we have the P waves and we have the S waves. The P waves, they occur longitudinally to the focus, and the S wave, they occur transversely to the focus. And you also have the surface waves that occur up and down. These waves, they can travel across the surface of Earth, and we can measure their essentially intensity. All right. The P waves and the S waves produced by the earthquake, they can be used to define the location and the magnitude of these earthquakes. But they can also be used, actually, and I think that's when I made the connection, to tell us about the Earth's interior. It can tell us about how the diameter, not the diameter, but the composition of Earth's interior, or the length, I'm going to put this way, of that core and the length of that mantle, okay, that we discussed. So P and S waves can be used to measure what's inside of the Earth as well. And that is because the P waves, they usually travel faster than the S waves. Okay, not they usually, they always do travel faster than the S waves. So, you can measure the time difference, that we're going to call the time lag in between those two waves, and you can tell them apart, and then you can calculate how far you are from that focus of that earthquake. Of course, you need a seismograph or a seismometer. You can't do that just like you would do with the lightning, okay? Just counting how many seconds you see the lightning and then the thunder. Here, the idea is essentially that, and I think the illustration makes a good a good case for it. The farthest that these waves travel, the greater is the time lag between the S and the P waves. So P waves, they travel faster, so you capture the P waves first, and then you capture the S waves, and then the surface waves, okay, which are the last to be captured. So the farther that you are from the focus, the longer it takes for S waves to arrive to your seismograph, to your equipment. So if you know the speed of these, if you know the speed of these two waves, you can calculate the distance from the source. All right. Not only that, but you can also use these waves to calculate the magnitude of that earthquake. The earthquakes are usually classified according to their depth in the Earth's crust. So we're going to have the shallow focus earthquakes, which are those earthquakes that happen down up to 70 kilometers deep into the Earth's crust. So, they occur down to that 70 kilometers into Earth's continental crust. Here we're talking about those earthquakes that are happening on soil, not on water. And these shallow focus earthquakes are they make up for about 85% of all the earthquakes that we experience or ever registered. Then we're going to have the intermediate focus earthquakes, and here you can kind of see what that word means, right? That's when the earthquakes, they are occurring in the uppermost part of the mantle, but they do pass that 70 kilometers into the Earth's crust, hitting the mantle all the way to 300 kilometers deep into the mantle. Usually not as frequent or as destructive as the shallow focus earthquakes, as you can imagine, because they are more buried into the Earth's interior. Then we have the deep focus earthquakes that will happen 300 kilometers down the Earth's surface. So they occur at the lower part of the mantle. Okay, so there is no earthquake happening down in the core that we know of. So that would happen mostly at the very crust or at the level of the mantle. All right. We can also measure the earthquake strength, right? And we use this Richter scale. Essentially, the intensity of this earthquake can vary from, a barely detectable earthquake to a widespread destruction. So the earthquake can be measured in terms of their vibrations, their displacement, and also the amount of the energy released. And you can think that, the larger the quake, the larger those waves, P and S waves and the surface waves will be recorded. And then from the size of these waves, we can assign a number. And that number is based on a logarithmic scale. I think it is, if you start from 1, if that wave is 10 times greater than what you categorize as 1, then that receives like a 2 point in that scale. I think that's kind of like the how the scale works. I'm not really sure, but each number kind of tells us how strong that wave was. So the larger the quake, the larger those waves will be, and the larger the magnitude and the numbers they will receive. Of course, we have a bottom limit here, which is 0, which there's a barely detectable earthquake, but there is no upper limit in this scale. I know that here I am showing the 9. The 9 is the largest or the most strong, the strongest earthquake that we ever recorded. I think it was 9.2, if I'm not mistaken, the most recent. But there is no upper limit because it's a logarithmic scale, so you can keep increasing that if we ever record something that is greater than this 9. All right. Usually those ones that are below 3, they are detectable, but they are usually not felt. And those ones above 3, they can be felt and some damage can occur. Usually we say that the higher the magnitude of that earthquake, the higher will be the energy released by the earthquake, and the higher will be the severity of the ground shaking vibrations. Okay, so the vibrations will be also greater. The greater is the magnitude. Okay, we have some examples here. I'm not going to go through these examples. I know that my table has the one in Japan as the 9 magnitude, but I do think there is one other earthquake that was registered to be 9.2. I just don't know its location off the top of my head, but you can definitely look for it because this is from 2011, so it's been a few years since this one was registered. I am also leaving you guys with, what to do in a situation of an earthquake. So please just read these instructions. I don't think here in our region we're gonna experience those earthquakes as often, but if you happen to go to California or some islands, you probably will appreciate reading this information. But always don't panic. Stay out of buildings that are damaging and try to find shelter. Okay. If you are outside, don't be close to those buildings because they can fall onto you, essentially. Also, stay away from glasses because they can shatter in that process. Okay? And after the shake passes, please do not go make a visit, do not go sightseeing because you're not touristing that area. That can still be dangerous. We also have the tsunamis. Tsunamis is just a Japanese term to describe ocean waves. We also have a term to those ocean waves that we can call the seismic sea waves, but tsunamis has been used currently, so it's quite acceptable. It is acceptable to use that to describe the seismic sea waves. So tsunamis usually happen when a section of the ocean's floor moves, and that section moves so much, pushing a great amount of water, such as an earthquake would push a lot of earth, right? A lot of earth in the sense of ground. I'm sorry about that. A lot of ground, right, through the vibrations. The tsunamis would also push a great amount of water. Usually normal waves are produced by winds, and they break at the shore, right? If you've been to the beach, that's how the waves are formed. I'm not talking about tides here, but tsunamis will occur when there is a very strong disturbance in the seafloor, especially around those plates, those boundaries, the boundaries of between two plates. Okay. The physical characteristic and features of these earthquakes they can reach up to 700 kilometers per hour in their speed, and they can have a wavelength up to 200 kilometers. So you can imagine how massive that is. Besides of the earthquakes and tsunamis, we also have mountains, right, that are related to these plate tectonics. These mountains, the definition of mountain is an elevated part of Earth's crust that rises abruptly above the surface. And these elevations, they can be formed by three main processes. Two of them we already discussed, which is the folding, right? So just think about the rug, and when you step, if you bulge up, that can cause, that dome, but if it bulges down, that causes the basing. So folding the sedimentary rocks can cause those elevations, for instance, or those valleys as well. Faulting can cause the orange of a mountain as well, like like I showed you in that picture, where there is the fault surface, one wall will grow over the other essentially. But volcanic activity can also create mountains. Most of the mountains, they do not occur alone. They usually occur in chains or belts, which is a group of mountains essentially. Here, this is a picture of the Appalachian Mountains, and like I said, the Appalachian Mountains were formed by this folding process. Okay, not only the Appalachian but also the Rocky Mountains and the Himalayan Mountains were formed by these foldings of the crust over time. So folding is a major feature of these mountain ranges. But what happened here is that over time, the crust underneath these places was submitted to a great compressional force, which we call that was a stress, a type of stress. And then that pushes all that earth together, okay, all that ground, all those rocks together. But again, the Appalachian, the Rocky Mountains, and the Himalayan, even though they were formed by these folded process, they are still suffering other processes such as weathering, erosion. Faults can also contribute to the changes in these mountains, so they are not mature essentially. That's what I wanna say. We're gonna study weathering and erosion in the next chapter actually. We also have the faulted mountains. This is an example of a faulted mountain. This is, I believe this is in Wyoming. That's the Teton Mountains, and I do think it is located in Wyoming. So when faults they occur, these faults will occur when there is compressional forces that shift a large amount of rock up or downward relative to one another. So you can see here that we have the fault planes, and when these blocks they move either up or down against or relative to each other, that's what we call faults, right? And if those blocks they rise above the relative ones on its side, then that creates a mountain essentially. I think it's very intuitive to think how a fault would create a mountain, and we call that a fault block mountains essentially, just because of their shape. Okay, of course there is erosion that can cut this block looking shape, but at their beginning that's what they are proposed to look like. So these compressional forces at the fault can shift up or down these rocks relative to one another, and they can create these fault block type of mountains. Okay, they can rise sharply along the fault plane. That's what's being shown here in this example. So you have the fault planes on both sides, and you have this one rising along the fault planes. But like I said, you still have some weathering that happens to these mountains, or even deposition of sediments that will change the shape of these mountains over time. Okay, I believe that some of the mountain ranges in Nevada, in Arizona, Utah as well, they also have fault block mountains that were formed in this process. But the main two chains of mountains in the US were formed by folding processes. We also have the volcanic mountains, and Here also the name is very suggestive. This is when the molten magma travels upwardly and piles up on Earth's surface, and it piles up to a point where the magma, as it solidifies, new magma piles up and solidifies, and then piles up again, all the way that it reach heights of equal to mountains that we discussed. So a volcano is essentially a hill or mountain that was formed by this extrusion, by this expulsion of lava, or rock fragments from the magma, from the mantle. Remember that lava is also magma, but it's the magma when it reaches the Earth's crust. Okay. This magma or this lava is usually deposited in this cone looking shape. So they are deposited in these conical shape, and then they have a specific structure. So you have the vent, which is the opening of that volcano mountain, so is where the eruption takes place. You also have the crater, which is the depression over that opening at the very summit of that cone. And you have the lava flow, which is when the lava is pulled out from that, or is pushed out from that crater and from that vent. So then you have these volcano formed mountains. Okay. Overall, I think this class is just very simple. So mountains or mountain ranges, they can be composed of many different types of rocks, mainly sedimentary rocks in the examples I showed you, and they can be formed by these processes called folding, faulting, or volcanic activity. Mountains are usually more apparent at where the plates meet each other at the boundaries, especially around or along the converging plate boundaries, where those two plates are trying to find, not are trying to find, they are finding each other, they are pushing against each other. You're gonna have the the orange of a new mountain range. I'm gonna leave you a question before I kind of do my summary of this class. How long does it take to build a mountain? How long does it take to build a mountain range? And you can tell me how long it took to build the Appalachian or the Rocky Mountains or the Himalayas, whatever mountain range you want to tell me. I will take. Make sure that you put that answer in your Cornell notes. I will be looking for that answer because I am kind of curious to see if you guys are doing some extra research besides of what I am telling you here. So overall in this class, we talked about this, principle of uniformity, which we can understand the past by looking what happens in the present, because the processes, the geologic processes that you see today happening to those rocks also happened to the rocks in the past. We talked about stress and the strain. So the stress are forces that will compress, pull apart, or deform a rock. Okay, but the rock can adjust to that stress, and we call that strains. So strains, they can be elastic, plastic, or breaking into a fracture. How the rock will respond to that stress will depend on the nature of the rock, the kinds of minerals that are present in the rock, the temperature of that stress that the rock is submitted to, and how quickly the stress is also applied. We talked about the earthquakes. We talked that these earthquakes are vibrations, right, that move out as waves, and we can detect those waves as P and S waves. And that happens usually because of the movement of those rocks. We also mentioned that those earthquakes, they have a focus and an epicenter. The focus is the very center, and the epicenter is above the center, essentially. And we talked about the processes that can create mountains, which are folding, faulting, and volcanic activity. So very quick and easy to study, very basic, simple concepts. Good luck.